My name is Steve Rees. I'm a performance guy from the lab up in Toronto working on LUW. If this title seems familiar at all, other than the fact that I ripped it off from a book, but it was a presentation just with this exact same title about 10 years ago in the DB2 8.2 time frame that was based on all the old snapshot stuff. And so last year I thought, well, it's time to update it because everything has changed in terms of performance monitoring and tuning and stuff like that in DB2. So it's completely rewritten. I think it's a lot simpler than it was with the new metrics and everything. It's a lot simpler. It's kind of, there's no rocket science here. There's no brain surgery. It's pretty common sense. But hopefully it's at the end of it, you go, no, it's not so bad. It's not a big deal to look after performance issues in DB2. So get started. We're going to kick off with some basic sort of foundation on things like goals and expectations, the core strategy we're going to take, the tools that we have, etc. We'll probably spend most of our time in this middle section here, system-level bottlenecks. Not necessarily because system-level bottlenecks are so common, but because the approach is going to be the same when you get down to statement-level bottlenecks. A lot of the approach is the same. So we'll spend time introducing it at that level and then extend it to system, to statement-level stuff towards the end. In terms of basics, so first of all, it's important to have a goal. We're not just gonna set off and do performance work without any idea of when we can say, okay, we're done. What are we trying to do? We're trying to close the gap, maybe after, God forbid, an upgrade slowed down some statement or something like that, or maybe you have some more data that's come out of the system or more users and things have slowed down a bit, where you need to create some headroom for more activity that's going to come onto the system. Knowing how much gap you have to close and where that is an important thing. But also really important, I think, is this idea that we're gonna try to act methodically. We're not going to just randomly change stuff. Well, I heard this at IDUG. I got to set this parameter to automatic, or I've got to not set it to automatic, or he said something about that. We're going to try to start off with having some data about how performance is when the system is running well. That's really important for comparison purposes. If you get users complaining and you don't know what's normal, it makes it really hard to get back to normal. When a problem happens, observe the data that we have, think about what could cause it, and then, if possible, change one thing or maybe a limited number of things at a time. You don't want to just throw everything in there because some could be good, some could be bad. In the real world, it's hard to do one thing at a time, but if we can be organized, at least be changing multiple things that are at least going towards sort of a coherent theory of what the problem is, that's better than just kind of randomly changing stuff. Okay, so various scopes of performance issues. Like I said, we're gonna start off looking at the system level. These are broad scope things where issues are impacting multiple users, multiple applications. You have many people throwing fireballs at you and making your life miserable, calling you at night, setting off the pager, tweeting about how lousy a DBA you are. And that's going to be where we start. As we focus down, we'll get to application level. We're not going to spend a lot of time here because this is kind of a gray area between statement level and system level. We're going to spend most of our time looking at statement level and then the system level and then statement level. Usually when we talk about statement level stuff, we talk about complex SQL, big nasty queries that go on for pages and pages and run forever. But it can also be those little tiny statements, those little tiny inserts, those little tiny point selects that are supposed to run in fractions of a millisecond. They start taking a couple of milliseconds, the whole system grinds to a sneeze, so it doesn't have to be 10 pages long to cause grief. We could get to the statement level either by somebody reporting an issue straight away, or perhaps we come down through the system level, just gradually drill down through the different layers of data that we have. The important thing is that the same basic approach works at all levels. And that is the idea that it's really simple. There's no rocket science here. Where are we spending our time? We're going to use the metrics that DB2 provides to determine where is those time spent. Why would I spend time tuning something which is not a big factor in the system? Why would I put air in the tires if the gas tank is empty? So we want to spend time looking at this. We're going to use metrics like the mon get functions, and I mentioned here about snapshots. I know a lot of people still like snapshots. They're handy things, but we've got to get on to the newer metrics. We'll talk about some good alternatives to that to get the kind of data that we need to be effective in solving performance problems. So we're going to use things like mon get workload, mon get buffer pool, etc. mon get database. We'll also use great shortcuts like like monReport.db summary. This is like a snapshot, except it uses the new metric. So it gives a nice breakdown of time spent, where is the time spent, how much am I waiting on, where am I waiting, all that kind of stuff. If I like reading human readable output as much as the next guy, and so monReport.db summary is my go-to snapshot for database replacement. And we're going to use that a lot today. Sidebar, the importance of delta values. Now this is one thing that DB summary does for us. And by this I mean, when I run DB summary, it collects some data, it waits some amount of time, it collects some more data, and then it reports just on the activity between the start and the end. So who knows, who cares what happened before I ran DB summary? It's just showing me what happened in between. Okay, if I don't do that, the table functions, they will give me data since the beginning of time, since activation of the database. There may be some cases where I want to know what's been happening for 6 months, but pretty usually I want to know just what's happening now, what the problem is actually occurring. Delta values are important. Here's some variety of details on one way to get delta values. There's some good suggestions, there's some good things that you can download from the IDUG website, from various blogs and things like that. This works pretty well. You don't have to worry about the details. Basically what we're doing is we're taking a collection, wait for a bit of time, and take another collection and calculate the deltas. The speaker notes for this presentation have the full queries in them that do all this stuff, all the DGTTs, all the data collection, all the calculations, so that you have something to start with. If you want to play around with these, it will do it for you. We'll get you started. You don't have to start from scratch. Anytime I mention a table function in here, I'm talking about deltas on that table function. I'm not talking just get what it gives you. Get the deltas because that's important. Okay, first thing I'd want to ask myself, if a performance problem was reported, is the problem inside DB2 or outside DB2? It's kind of like the iceberg question. Are we above the waterline? Client idle wait time is a metric that you can get. It reports the amount of time spent waiting for the next request. Okay, so that's the time above DB2. The time below the waterline is total request time. So if the top, we kind of have the top picture here, this is what people would normally assume most time is spent in DB2. Fact is that ratio between those two is often 5 to 10 times more above DB2 than below. So it'd be like a styrofoam iceberg. It'd be just sitting up there on the water, no problem. So this is a really good first thing to check, because it's always the database's fault, right? You check this and say, well, you know what? We're spending 20 times more time above DB2 than inside DB2. It could be network, it could be application, who knows what it is, but it's not a DB2 problem. Where to get this information from? Here's a snippet from monReport.db summary where it shows the metrics that we want. The first one is request time. In this case, it was 11,000 and change milliseconds to client wait time, 118,000 milliseconds. In this particular case, a ratio of 10 to 1. 10 times more time above the waterline than below the waterline.
So this is a question on that. Is that affected by the number of connections or clients that are happening at the database?
Short answer is absolutely yes. So the question is it affected by the number of connections? It is. It's a total across the whole database. So that's where I get to the bottom here with a bit of a warning about using DB summary for this. Because if I have, Joe down the hall likes to have 10 sessions open, 10 CLP connections into the database at all times, just so we can go to any window he wants. All those idle connections are accumulating client idle wait time, which we don't necessarily want. It's going to bloat this ratio. So if you're in an environment like that, better thing to do is go to our good friend on the connections. Simple query across that to rule out anything that's not, any connection that's not doing any activity at all, no requests or activities or anything. Just leave those out of the total. Do your sum where activity is greater than 0, and now you've got a true reflection of the actual activity on the connections. And you can get arbitrarily more picky if you want. You can filter it down to the accounts receivable application or the SAP application or whatever's running. You can filter it down that way to see what's going on for those guys. Okay, so assuming that it is a DB2 issue, for the sake of argument, the time spent breakdown in DB2, it breaks down to two basic categories. Are we processing or are we waiting? Processing is good, waiting is not so good. Waiting is typically much bigger than processing. The definitive list of all the different wait times that DB2 provides is in the Knowledge Center. We all know that the Knowledge Center search is terrible. But if you use these keywords, time spent hierarchy, it will actually get you to something useful. It will get you to a nice indented list of all the wait times and what is a part of what, etc. It's a very good thing. I actually have it bookmarked in my browser. Wait times tend to be more dominant. Things like I/O, communication, locks, and latches, and all that stuff. Processing time, there are fewer categories. We'll get to that in a minute. We're going to spend more time looking at wait time. In practice, we just look for whatever is the largest. I'm going to go through a bunch of different wait times. It's not like to do this process, you would need to necessarily step through everything. You just look at the ones that are coming up big. When we go to DB summary, you get a nice breakdown of time spent. Here it's showing you that about 86% of request time is spent waiting. 20 to 30% I would call normal. Okay? You know, there's I/O, there's locks, there's a certain amount of waiting in databases. 20 to 30% is not bad at all. 80 to 90%, that's definitely something to look into. Now, how to break that down? This is the breakdown that DB summary is going to show you. It says total wait time is 100%. First of all, my system is not 100% on it. It's just saying of the wait time you have. This is how it breaks down. We got to keep that in mind. That's a different sort of definition because we're going to get into percents, which is a bit nasty. So at the top we have I/O-based ones like buffer pool read time, direct read time for logs, that kind of stuff. We got lock waits, we got I/O stuff, or communication stuff, which is handy. We're going to talk about FCM and TCP/IP in a minute. And if you're a pureScale guy, like Kit, you've got pureScale metrics in here too. Now, the very clever people in the audience will notice that this does not add up to 100, even close. Now, I didn't snip any off here. It's just not there because the DB summary does not show all 25 or 28 or whatever it is kind of wait time. So sometimes you may notice that the total does not add up and go, okay, there's a kind of wait time in my system that is not showing up in this. I've got to dig a little bit deeper. I'll talk about how to do that today. Okay, so taking this for an example, pool read time is the big hitter here, 52%. This would be the logical place for me to look. So let's start with that. Pool read time is just the amount of time spent reading pages into the buffer pool. It's typically synchronous reads. It's not, it doesn't include prefetcher time or anything like that. That's different. So it's just synchronous reads. Two possible causes to high pool read time. Either I'm reading too much or each read is taking too long. Which is it? You gotta figure that out. First thing we do is we check the average read time. We go to non-get table space. It gives us a breakdown of I/O time and lots of great statistics per table space. And the little box up here says C speaker notes, the whole query for non-get table space, including the deltas and stuff, is in the speaker notes. If the average time is more than about 5 to 10 milliseconds, I would call of a busy table space or something that's doing a lot of work. Okay, I would call that a bit high, and that could be what's behind my 52% pool read time. The nice thing about doing it against non-get table spaces, I get a breakdown across all table spaces. I may have different table spaces on different storage groups. I may have some table spaces on SSD. I may have some table spaces on cheap, enormous spinning SATA drives or something like that. Knowing that breakdown is really helpful. On the other side, if individual reads aren't taking so much time, we look at the number of reads we're doing. High number of physical reads, low buffer pool ratio are going to be something that we want to look at. And here's where we first take we stick a toe into statement level analysis. We think about looking for statements that are driving a lot of I/O. Why are they driving so much I/O? Is there any way that we can improve the plans, etc.? We'll get to that in a little bit. Another really common kind of wait time that we're going to see is lock wait time. DB summary gives us just the high level number. It says 14% or whatever, but it doesn't tell us anything more after that. Fortunately, there's another report called lock wait, which gives us a great polar waiter kind of report. based on what's happening right now. This application is holding, this one's waiting, it's a row lock on this table, it's held in X, it's wanted, it's desired in shared, all this information about the lock weights that are going on right now. Only right now. If it's something that, it does not give you like the last hour or something like that. So you got to hit this thing a bunch of times to kind of build up a picture in your head of what the lock weights look like over time. You do not want to jump to any conclusions based on one sample of this, saying, oh, well, there's a big lock weight problem because I saw it happen once. If you really want to turn it up to 11 and get the full Monty version of lock weight information, lock weight event monitor is the way to go. Obviously, with some asterisks and caveats and appropriate things around it. Now, we can use this. This will basically give me a trace of all lock weight events based on the threshold that I set. So if you're concerned about overhead, we can start with a high threshold. Maybe don't fire an event unless the lock weight gets to be 10 seconds or something really huge. And then maybe tighten it down, lower it down to pick up a little bit more, conservative approach to try to pick up get the information you need without bogging down the system. You can also ask the lock weight event monitor for information like what SQL statement was it, what parameter values were passed into the SQL statement that's causing this massive lock weight. But you're going to really want that data because the overhead is not tiny. Let's hand it again. Okay, a couple of basic tips to reduce lock weight. Obviously selective access. Like I said, no rocket science here. If my plans are going against indexes or partition tables or MQTs or something like that, if things are a little bit more selective, it means fewer locks means less potential lock weight. Lowest isolation level permitted by business requirements. We can pick up the isolation level in use out of one get package cast statement. I'll mention a little bit about currently committed. This is sort of writer's blocking readers problem. Somebody comes along, updates a row, doesn't commit. It's got an X lock on that row. Somebody else comes along, wants to read the row, and it's got to stop. Well, since 9.7 by default, we enable a feature called currently committed that allows that reader to get the currently committed value out of the log. It's pretty cool. Works best in non-partition, non-cluster versions of DB2. On pureScale, we can only get out of the local log of the current member, but still pretty helpful. It's the default, yeah, but I mentioned it because if you've got a database that's been brought forward from 8.2 and migrated and upgraded and whatever, we would not have defaulted this on for you. So this might be something that you need to enable explicitly if you're migrating forward an older database. One more tip about this is eliminating long commit delays. So we've got applications like batch applications, etc., that are doing a zillion operations, collecting locks like trading cards, and then not committing. They can be the 800-pound gorilla in the system that is just, other applications are walking up behind them, and it's just a terrible thing. So, if we can commit frequently, that's obviously the best thing. But the first step is find these guys. So if I have a lot of lock weight time, I might want to go into one get connection with the individual connections in my system. And from this, I can get all kinds of information like the application name, the IP address, and everything. But, as for who is the culprit, I go after numlocks held, big number. Okay? Application handle regularly showing up in on report.lockweight or on the application lockweight. Total app commits are not increasing. That's the signs that an application is misbehaving in terms of accumulated locks and not committing directly. Log disk wait time. So this is kind of an interesting one because this shows up way more than people would think it would. So log disk wait time is time not just to write to the log disk. I think we named it terribly because it kind of implies there's a disk involved or something. And there is, but there's a bunch of other stuff. It's the time for the agent to communicate with the logger, for the logger to wake up and do the flush and get back to the agent. So there's a bunch of stuff going on there, plus HADR, if you happen to be using HADR. So this number can get quite high. Sanity check number one, and it's not going to contribute to this. The good thing I like to remind people is making sure that your log buffer is not filling up. The good size is about 2K. I've seen some at 50K or 100K because people are trying to buffer their entire log file. No problem.
I assume that's synchronous only.
Is
it HADR would be synchronous only, would be the log.
Next page.
Oh, sorry.
You're totally right. When you average log disk write time is a good thing to check. If this number is higher than you think it should, table function recently added called get transaction log. It kind of fills in the blanks of a bunch of logging metrics that are handy. So what we discovered, log write time by num log, right? I always get the average log write time. We're looking for something in the neighborhood of 2 to 4 milliseconds. Or if you've gone, to SSDs or something, it would be even lower than that. It could be a millisecond or less. But if the numbers get high, 2, 4, 5, 10 milliseconds on a busy system, that would be a sign that your logger needs a bit of TLC. Okay, on to Kent's question. What about HADR? If I'm in a case where I have large or high log disk wait time, so that circle of life between the agent and the log writer and back to the agent, but my individual log writes are quick. Maybe they're on SSD. Could be HADR. Now, as Kent mentioned, you made the point about it's the sync level that matters, and it does absolutely. If I have sync level at synchronous or near sync, then there's going to be potentially some pressure on commit coming back on this. And what we can do is we can figure out, we can compare the average log disk wait time, which is the metric the calculation we just talked about, versus the HADR wait time. We've got the two sets of calculations here. HADR time is a substantial fraction of my log disk wait time. That tells me exactly where the time is going. Again, with the philosophy of where is the time being spent. Because now I won't worry about my log disk so much. I might look into network performance between the primary and the standby. I might look at, if I'm running sync mode, I might look at the log device on the standby to make sure it's able to keep up. The whole fairly complicated organization of moving parts going on there, all initially led to by this one metric. Direct read and write time is incurred when we do log or long varchar, that kind of thing, or XML. Now, if anybody's using long varchar, it's deprecated. Okay, so all the investments in large stores that we've done in DB2, non-buffer pool kind of stuff, has been into logs and XML. Nothing has gone into long varchar. So if you're using long varchar, you should consider moving either to a big varchar, big plain varchar, or to anyway, but let's talk about direct I/O time. Direct I/O does not go through the buffer pool. Direct I/O just goes between the disk and the agent, etc. Prefetchers can get involved in some cases, etc., but I want to keep it a little bit simple for now. If we see high direct I/O time, probably what we want to do next is look at individual table spaces because the I/O can be different across those. One thing that can impact log I/O performance is whether or not the table space has file system caching enabled or not. It can be a good idea sometimes, it can be not a good idea other times, but it certainly can be different. So going across table spaces and storage groups, looking at performance that way is a good next step to consider. We also want to look at requests. So some bright light back when DB2 was first being decided that a direct read is a 512 byte thing. It's not like we do 512 plus IOs, but it's an accounting thing. They're called direct reads and writes, 512 byte segments, which is totally pointless because the world doesn't work that way. So I prefer direct read requests, direct write requests. These are the counters of the full log operation. So that's what really matters. I mean, if we're looking at something like 100 kilobyte log read request, I would expect something 10 milliseconds, give or take, a little bit less. I don't care how many 512 byte sectors that is. I just want to know what's going on with the actual log request. I see some of these. Probably what I want to do is look at the statements that are driving these and see if there's anything to do with the statement or with the table that's around, and that comes back to inlining. Inlining is probably the best way that we have available to us to deal with logs, smallish logs. Not going to be a gig, they can be 2 gig or whatever, but in the real world, most logs are like 5K, 10K, 20K. They're not usually enormous. And if they're small like that, then we can inline it into not a piece of a log, the whole log has to fit. And if it fits for a particular row, it's in there, and if it doesn't fit, it's out in the external storage or the separate storage, the log storage. It all happens under the covers. It's kind of cool. I like it a lot. The tricky thing is how do I tell inlining the row. If the table's in a 4K page, then I have at most, I can make my row at most 4K bytes long, give or take. So I can, maybe I'm limited to how much lob I can fit in there, maybe it's not that much, maybe none of my lobs will fit in whatever's left over there. Maybe I can go to 8K, 16K, 32K page. Increase the page size might let me put more lobs into my row, and this can be a game changer. If your system is dependent on lobs, use a lot of lobs, you spend a lot of time in direct I/O. This can be huge. Simple little query here helps you tell how many rows, how many lob values will fit. If for example, say I said, well, I'm going to have at most 5 kilobytes inline. You know, this is just counting simple stuff. It's no rocket science. Just counting up how many lobs are going to fit. But hey, what if I increase maybe from 8K to 16K? Maybe I can now inline 9K, 12K, or something like that, and fit in more. If I could cross that, is that, you know, a rule of thumb, you could say 75 to 90% of the lobs within, if you can get them inline, you're going to see, I'll say better performance. There's always an asterisk, right? If I'm inlining a ton of stuff, it can be good. But it is going to take up buffer pool space, right? It's going to take up footprint of my buffer pool, and if that starts pushing out important stuff, then maybe I need to balance that off. Maybe I can add a little bit more memory to the buffer pool. Maybe I can do something along those lines. It's not something you can just blindly do it and it's going to fix all your problems. It needs some careful consideration. There is more to think about here. I've got a link in the presentation to, you know, I think it's 3 or 4 pages on this stuff that you can get a little bit more detail on the trade-offs, but it's definitely something worth looking into if lobs are big in your system.
One question.
Yeah.
Compression on logs is not really a key DB2 feature. You can have the table compressed and all the other tables compressed.
That's correct. So the question, the remark in general was about compression of lobs, and that was something I didn't mention. About, you know, one of the virtues of getting into the buffer pool is all of a sudden, you know, prefetching works for you, HMing works for you, compression works for you. All these things that behave as, you know, a particular way with non-lob data, all of a sudden are acting in the lob data that way. So it kind of promotes it to real data, not some kind of stuff that's out there somewhere and we don't really need to worry about.
Steve, can I ask one more question?
Yeah, sure.
So I guess when did it 10.5 you got expanded row?
10.5 expanded row.
So if I mark that, I mean, it's by default it's on. I created anyways. So now a row can span a 32K page. Does that affect the size of the inline at all?
So the question was about expanded row, which will let you have a row that's bigger than your page size. Basically, by taking, you know, by putting an overflow into lobs. So if you're considered about performance, extended row is not a super thing. I mean, it's great to have for that 0.1% of the time, where a row will overflow. You know, so that you don't get an error. That's great. But if the row is overflowing 50% of the time, that is going to kill your performance. Because now all of a sudden 50% of your rows have a big chunk of lob on the top. Now as relates to this in inlining, I don't think we're going to get any interference between inlining of a lob and extended row. Next thing, FCM time, which, you know, if you're running DPF, you've seen FCM. Fast Communication Manager is a piece of DB2 that's in charge of moving data between subagents that are working on a shared task. If you're in DPF, you've seen this before. You've seen things like, you know, send wait time if the receiver is busy. Generalization. You know, if the receiver is busy or slow or not ready, then send time will accumulate. If the sender is slow or not sending yet, then receive time will accumulate. These numbers can get big. They can get big pretty fast if it's a big query. It's not necessarily something to worry about. Okay. It's also interesting to note that, by the way, that, you know, you can see that in totally non-parallelized systems. You're on some OLTP system with no SMT enabled. You can still see this crop up because things like reorg and create index actually spin off subagents. So the coverage, you don't even know what's happening. And they use FCM to talk to each other, which can drive a little bit of FCM weight. And you're used to seeing 0 there, and all of a sudden you see a little bit of weight, you wonder, who spun off this parallel query from the system? It's not necessarily that. High high FCM time can be benign. You know, we're not trying to get it to zero because we think about cases like the coordinator agent. He's just waiting for data to come in from the sub agents, and his meter's running. You know, there's no way to make him go do something else useful and not just count up FCM time. It's just the way the architecture works. So seeing FCM time accumulate is not necessarily a bad thing. It could mean some bad things. It could mean too many messages. So if we've got a poor partitioning strategy, we've got lots of broadcast joins in the system, stuff flying all over the place, that could drive up the number of messages and hurt our overall performance. If we've got a little bit of time and inclination to figure out the command line options with the DB2 design advisor, it can give you advice on how to change your partitioning. It can also be network bottlenecks. So this is a little bit harder to sort out. I mean, you make friends with your network administrator, you buy him or her a copy, and you try to figure out, you know, okay, what's going on? Can you run some tests with AIM or IPERC or something like that to figure out is the network acting according as well as with throughput as it should be for the configuration engines. You know, if it's a 1 gigabit, if it's a 1 gigabit network and it's only operating at 80K. Tom, question?
Would the TCP IP wait times do something to compare this with? Or is FCM waiting for network to get a TCP IP wait time?
That's a super question. They're quite related. So the question is, how does TCP and FCM relate to this today? They could be correlated. I mean, if you had wide network problems, you could have network problems impacting FCM time and also TCP client server wait time. A lot of the time they're different networks. The client server network is often larger than the FCM network, but yeah, I mean, they could be correlated. Let's talk about prefetch wait time. This is another one where you could have monster size numbers, like 9-digit numbers of prefetch wait time. What's up with that? How bad a situation is this really? First of all, it's not reported in DB summary, so it could be one of those missing from the 100% things. I wouldn't call it that absolute most important one on our list, but it's good to know what's going on. It accumulates when an agent goes to read a page that's already a prefetch request set for. So I go to read page 1, page 1's already being prefetched. Okay, now my prefetch wait time counter starts running. Some amount is pretty normal. 0 isn't always best. 0 probably means that you're not doing any prefetching at all, and that prefetching is usually a pretty helpful thing. Okay, so not 0, not astronomical. If it is the dominant thing in your system, then you probably want to get into it. But it isn't basics to check. If the numbers are really high, we can look at the actual prefetch size in pages. We can look at the configured prefetch size for different table spaces if it's configured too small, or if the number of prefetchers is too small. That can all contribute to poor prefetching performance, of course, as could poor storage performance. TCP/IP send and receive time. This is one that I've seen more frequently in the last year, to be honest, because cloud, hybrid cloud, database server in Dallas, application server in San Jose could be totally fine unless they're super chatty, unless there's a ton of traffic going back and forth between them. We can't fix physics. We can't make the network between San Jose and Dallas run faster than its the speed of light. So this can start to add up. This is different than client idle wait time. This time only starts running once we start flowing data over the network. It's typically send wait time is more common than receive because that's DB2 pushing out a result set. Okay, to the client. Blocking cursors are DB2 will almost always choose a blocking cursors if it can, but in some cases it may need a little bit of encouragement. So this is a good thing to check into if you're pushing out big result sets. Optimize for n rows on very large data sets is going to limit the size of the blocking that can be done. So if you say optimize for 1 row on a billion row result set, you are going to get no blocking. You're going to get 1 row at a time. You're going to get terrible performance. If you decided for some reason this was a good thing, but it could happen. Okay, so here's some thoughts about the networking, really. And again, this is kind of outside our typical domain of expertise. Maybe it's outside mine. So I would tend to go for things like, I talk to our network guys. Something like IPERC, which is a nice simple tool for downloading and testing throughput. I mean, we can go for ping, but you'll get more credibility if you have IPERC data and it says know my 1 gigabit network is actually running at 50K a second. Why is that? So we're comparing against the configured size and also seeing what DB2 can do. You know, a simple query driven with DB2 batch. So there's no overhead. We say minus OR0 DB2 batch. Fetch everything but display nothing. A nice wide result set. All the blocking I can get. Give DB2 the perfect circumstances for good performance. Does its throughput approach what iPerf can do, or what the network is supposed to be able to do? If it doesn't, then there's a gap there that we got to understand. Now we start to get esoteric. I'm not going to go into this too much, but latch wait time. We started reporting latch wait time in our metrics, and people want to know what latches are. Latches are something that's present in any multi-threaded program to keep 2 threads from updating the same piece of memory at the same time. They're not a lock. It's different from that. DB2 is full of latches. Firefox is full of latches. AIX Linux is full of latches. It's inevitable. And we spend a lot of time trying to optimize the protocols we use for latching to make them as sleek as possible. It's like timing all the green lights, you know, so that we don't have everybody backed up at the intersections. We want that traffic to get through as quickly as possible. So there's some details here, and a lot of this boils down to you have heavy, consistent latch wait time apart from the next page. And this is probably something that you're going to have to talk to DB2 support about, because it's you know, talk about no serviceable parts inside. Okay, but I'm going to show one case where we can deal with a latch wait at the user level. Okay. This one is about buffer pool latches, and this is actually a pretty common thing when we end up with latch problems. So suppose at the database level it says 50% latch wait. Holy cow, what's going on here? Step 1, DB2 PD-latches. I don't know if we talked about that in our presentation. Or we can go to get extended latch wait. A nice table function gives you a nice formatted thing. Now, every latch has a name, and the name is a string about this long, and it's gobbledygook, and it doesn't really mean much. But we can look for a clue in there. If the latches have component names in them, SQLDB is buffer pool. That's our secret decoder ring name for buffer pool code. You might see some of these latches. You see it at the very top of the list. High contention on a buffer pool page will show up as an SQLDB latch. Now, I will say that version 11.1, we spent a whole bunch of time making big improvements in this area. So this is one exciting. Those you know, DB2 transactional throughput improved by X% perhaps, and we saw in the keynote today. Those were because of that latching change. So that's a very cool thing. And I'll talk a little bit more about that on Thursday. Anyway, so SQLDB latch thing, tons and tons of agents and threads are just beating on one page, even just trying to read it. And you know, friction builds up, and the page heats up, and we get contention. A lot of the times it's an index root page. You know, think about the number of queries that have to start up at that root page and find their way down. Even if they're doing something really simple, they got to start at the start. So what can we do about this? So we know it's a buffer pool latch. How do we figure out what table we're talking about? We go into, we look at the statement level. Want to get package cache statements? We look for statements with high extended latch wait time. That gives us an important clue to what table. What do I do about this? If I can partition this thing, if I can range partition the table, if I can introduce local indexes, basically what I'm doing is I'm spreading out, I'm parallelizing my table, I'm parallelizing my index. A lot of the times the latch wait time will just disappear. And if it doesn't, the friendly people at DB2 support. Alright, a couple of things that are super esoteric, and I want to mention because they do show up. One is audit wait time. If you have audit system enabled with no audit buffering, so everything goes to disk. There's a recipe for slow. If you like slow, this is a great way to achieve it. Another log wait time. If you get DIAG level 4, you know, lots of informational stuff pouring in. If you're in a clustered environment, pureScale or DPF with a common DIAG.log file, this is another recipe for, you know, there's a lot of stuff going in, and it could cause back pressure on the whole system. So there's typically easy ways around it. You know, where do we put the DIAG log file? What's our DIAG level? That kind of thing. If I'm in a cluster, having separate DIAG.log files per member is an excellent thing Alright. So to just review our wait times, the typical ones we see in the DB summary, pool read, walk rate, log disk, etc. A few more that we don't get in DB summary, but we get from the database. Or it's not all about waiting, it's about processing as well. So processing, as I mentioned, there's not as much to it as there is about wait time. There's a couple of things. Two things that made out: section processing, which is the useful processing of statements, etc., and compile processing, necessary stuff, but if it gets away from us, it can be responsible for consuming a bunch of CPU. But old DB summary gives me a breakdown and even reports compile processing. My own rule of thumb, I would say more than about 10% is something along like this, because 17% of time is being spent compiling SQL. Compile processing time could be these complex SQL, could be normal and unavoidable in your environment. If the optimization level is cranked up, that might contribute to it, but it might just be the cost of doing business. And also, and I see this a lot, so I keep mentioning this every year about the applications which drive almost duplicate statements that differ only by literal values. You've just got to compile everything. And that takes up package cache space, that takes up the CPU and the compiler. It's an expensive thing. And so, we can detect that, at a high rate of package cache inserts. There's also a metric added in 10.5 called statement ID. It's like a hash value that the compiler produces that will produce the same value if the only thing that differs between two statements is literals. Okay, so we can basically look at the number of distinct values. And if it's low, if the ratio between total statements and number of distinct statement IDs is high, then I've got potentially got a problem in this area. We talked about statement concentrator and stuff like that in the past. So I really just say that the best fix is to use parameter markers in these cases. That's just the best fix. There's workarounds, but they're just band-aids. Better to fix it at source. High section processing time. This is where we want to spend our time doing our work. This is the actual heavy lifting that the system is supposed to be doing. But if we are running out of CPU as a result, we probably want to understand where the CPU is going. A few things that can increase CPU usage that we want to be aware of. One is compression. Compression is generally a performance win. If you factor in all the bits and pieces, the space saved on disk, the I/O traffic coming in off disk, basically the virtually expanded buffer pool. Now I can fit more rows in my buffer pool. There's all kinds of reasons to use compression. But it is not free. It's not computationally free. It could be the difference between running it, 80% and 95%. Lots of people are comfortable at 80% CPU and not so comfortable at 95%. So that can be the difference. Encryption is similar, but it's a little different. Compression, we incur the processing costs every time we refer to the row, but encryption is an I/O thing. It's like an extra I/O cost. So once the page is in the buffer pool, it's already decrypted. So we only have that cost when we write out the page. If the page got dirty, then it will be decrypted, and it will be re-encrypted on the way out. So it tends to have a lower overhead, but it really depends on how much you can keep in memory. If you keep lots in memory, or if you can have selective access plans, like table scans, you can imagine the amount of decryption you have to do, just ripping through a whole table, decrypting every page. That's expensive. Extra motivation. Better access. Last one I want to mention is client-server code page differences. We used to see this quite a bit, don't see it too much anymore. Differences, we have client in one code page, the server in another code page, and we'll all sort it out. We'll do everything we need to make sure the data is readable going both ways. But the translation can be expensive. Because lightweight things like Windows and IX, you hardly even notice that. No problem. The differences are almost indistinguishable. Sometimes there's more complicated ones, UCS2 or UTF-8 code pages, things like that can be much more expensive to translate between. So if your enterprise is truly global and you've got databases spread around the world and you've got to have data from a variety of languages in your database, this is going to be a bit of a challenge. It's not the only challenge you'll have, of course. Collation and that kind of stuff is interesting as well, but it's something to be aware of.
Compression. This time with blue. I understand with blue you don't need to decompress the credits being evaluated on the compressed data.
So the question was about blue, and is it not true that blue doesn't decompress on evaluation? And you're 100% correct. That's a good distinction to make. So this is primarily about row-based compression. Although, compression in blue is not free either, but you can turn it on. So it is like income tax. Good luck getting rid of that income. Okay. Statement level bottlenecks. So we talked about this. We talked mostly about system level bottlenecks and where time is spent and as a way to approach this, and we're going to do exactly the same thing for statements. You can either end up here because somebody's complaining about a poor running statement, or because we had a few examples in the first half of the presentation about coming down, for lock weight. Okay, go and look at the statements that incur high lock weight. So the two aspects of looking into this are almost indivisible. Fundamental process is exactly the same. Find out where time is spent. Some of the details are a little different. At the statement level, it's about activities versus requests. And some of the things that we saw at the system level, like TCP wait time, do not apply at statement level. So we don't even see it there at all. Something that everybody in here knows, but I want to remind it anyways, that we're going to get into explain plans and things like that. Before you pull your hair out, looking into explain plans, making sure that your statistics are up to date is a really good first thing to do. If they're wrong, you're giving a bad plan. That could be all it is, and you can save yourself a bunch of time.
How about solving a specific problem, and that is, whenever you run stats on a heavily active table, you often get an error, a message back, a warning message back saying that the statistics are not, for indexing is not equal to the statistics collected for the table.
So Ken's making the very correct remark that sometimes when you run stats, you can get complaints back about inconsistencies between statistics collected in different ways, and that tends to be with the broader scope, more sophisticated run stats, like we're getting indexes and there's stuff going on at the same time, etc. I'm going to stick with the simple-minded recommendation, and there's a whole bunch of asterisks about okay, run stats, with how much sampling should I do, when should I do it, what kind of statistics should I collect, and what do I do about these, what do I do about these warnings, but I'm going to have to gloss over that for today. Sure. We can have a beer and discuss it. In about 10 minutes. Okay, so data to diagnose expensive statements. We talked about monoport.package cache is a nice, simple report, easy to read. Gives me, 3 or 4 top 10 lists, things like number of executions, CPU used, rows read, all these kind of things. It's you want a quick and dirty report. This is pretty cool. It doesn't help us after that, but it will get us started kind of the same way that DB summary got us started. Instead, we are going to go to the great big bad get package cache statement, like 350 columns of everything you could possibly want to know about statements in DB2, including some metrics that we don't even fill in yet. Again, like most other monitor table functions, these delta calculations, and all the examples I have here already have that stuff built in, but it's important not to just use what it gives you to calculate the delta. Okay, so supposing we were coming at this from a system level, and we had kind of built up our virtual pie chart wait times, and something like this time set for DB. Database level, a bunch of wait time, maybe that's your pool reads and processing time, etc. It could be a true system level problem, or it could be a handful of statements causing, wrecking it for everybody, causing a problem that causes the system to bog down. How do we tell the difference? And the easy way to tell the difference is we go after maybe the top 10 statements by activity wait time. If it's a true system level problem, then probably all my statements are going to be impacted probably in a fairly similar way, whereas if it's 3 or 4 bad actors, they're going to stand out right at the top and go, look at me, look at me, look at me. So we're going to look at it that way. Monoport.package cache, again, it's nice and quick and easy, but we can't go any deeper, so we're going to get most of the deep dive information from get package cache. So an eye chart here with lots of decimal paths. Don't worry about the details, it's all in the sleepy notes. But just to point out the high-level stuff, we're just going to pick up just like package cache does things like number of executions, overall time spent waiting, lock wait time. In fact, if you want to go full on and get audit buffer wait time and diaglog wait time, you can just add them to this. They're all available in MongoDB package cache. Totals versus averages. This is interesting because MonReport.package cache gives you both. And sometimes you want one, and sometimes you want the other. So I would suggest you get both. And we're just going to talk a little bit about that. When I say totals, the package cache and MonGet package cache statement, you know, might say there's 1,000 executions of a statement, and the metrics it gives for that statement are the totals for all executions of that statement, which can be really handy. You know, am I being crushed by boulders or by grains of sand? Am I being crushed by teeny tiny insert statements that take less than a millisecond to execute, but there's a billion of them running an hour? Or is it some big nasty query? Those are both very plausible in those systems. So having the totals and the averages is very useful. One of the totals, I mean, another thing that helps us out here is even just knowing the number of executions can be a valuable clue. Is it executed only rarely? Is it executed all the time? Should I go after it? Is it particularly nasty? Averages, that's where averages are going to help us out. You go to, on the average side, I can tell the difference between a fairly bad statement that's executed a lot versus an absolutely tragic one that maybe only executed once, but boy, when it hits the system, everything is totally grounded. Having the two of those is important. I think this is probably the most important reason to have averages, which is it's insensitive to the amount of time we're collecting data. So maybe sometimes I have a minute's worth of data, sometimes I have 30 seconds. Maybe I change my policy to 5 minutes. The averages won't change a lot. Obviously, the totals could be all over the place, just depending on how much data I've collected. Okay, so I took that query that I showed a couple of minutes ago, and I ran it on a system that I had in the lab, just to get an idea of, you know, just as an example of what's going on with particular statements. So we can make a few observations here. A number of executions here, so it's a fairly busy system. 5,000 executions during the sample time of like 30 seconds. For many different kinds of statements, one of them is much busier, 60,000 executions. Percentage of wait time, so 80 to 90% of my request time is being spent waiting. So this is clearly not a super healthy system. Of the kinds of wait time that I showed here, block wait time is clearly the one that's giving me the most grief. So this is, I can learn a fair bit just by looking at this. But also, if I cast my eye to the particular statements, the statement text over here, I notice that almost all the statements, 7 out of 10 of the statements are on one table. I see common references to column names, to a particular table, customer. So, you know, between knowing the details here and the fact that it's all on one table, that gives me an excellent start of where to go next.
Why does a select have a 0.02 log weight? Percent log this 0.02 on a select.
That is a super question, to which I do not have the answer. And it makes me wish I had edited the output. If I don't edit it,
Another one for us, where you could have sorts and it could spill over.
yeah, we get totally right.
No, log. But a log is active log.
I know what's the rest of that statement looks like, and there should be no reason it's long. So I'm curious too. I'm gonna go look it up, and when I come up with the answer, I'll have volume 7 of performance. Did you know?
Well, what if currently committed is turned on and is reading a log? Maybe
Currently committed.
The percent log at disk is the active log time.
I think that's log flush time. I think that's log read time. So that's a good answer.
And also you've got system tables. So if you select from a table, at some point it's going to be updated. The last used column, for instance, in the system table, there are some system tables that are updated on the select.
There's a whole bunch of great theories here. I got to figure out which one it is, but I don't know for now. So I'll come back to this. I'll put it in the blog post. But dear Cam, wait times at the state level. How to look into this? So we've got MonReport.lock wait, which I mentioned at the beginning, that goes into that nice holder waiter stuff. Very helpful. But we've also got MonGet application lock wait, which is another point in time thing. Or external tools, data server manager, there's lots of other great tools around that are going to help us look into that. Again, also using the knowledge that we gained from looking at our simple query, that it was one table that was involved, cross-referencing all of this stuff. We got all this information, we know it's lock weight, we know the table that's involved. We can see that a lot of customer table row locks are being intended. Okay, so that doesn't help us all that much, maybe helps us a little bit. We get some hot statements that have high lock weight time to refer to customer. Are they any of our other bad actors? We can look them up in our other top 10 lists like CPU and rows red and all that stuff. There's probably a bunch of people here that are thinking, you know what, you just dropped an index and it's going to be a table scan and that's why we're getting lock weight. But interestingly, this is not in the top 10 of rows red. So this isn't the super simple case where an index was dropped and now we're table scanning. This is just a tiny bit more sophisticated. This is about the time to crack out the access plan. And so one thing I want to mention here is, you know, it's very tempting to just cut and paste that statement into the command line and DB2 explain or die explain. You can still get to run. DB2 explain is the less desirable way to get access. DB2 EXFNT is where it's at. And it's a good thing to know because there's so much more information in DB2 EXFNT. And if you get involved in talking to DB2 support, they're going to want to see an EXFNT, not an explain output. And there could be times when they don't differ in the bones of the plan, but it's like they can be telling you different things. It feels that way. Anyway. So, how to get explain out of the package cache. I love this. Long get package cache statement with a column called executable ID. It's a 32-byte binary mess, kind of binary, hex mess, that we then plow into explain from section. We call this for procedure. This populates the explain tables for us based on the exact statement that was running in the package cache, including the compile environment, including the isolation level, including all those things that can give different plans. And then we run DB2 X17 to get the output. I'm not going to show that here, but a little bit of observation of the plans shows that all those 7 statements had in common. They had where C1 equals C2 to C3. And the index that we're using was C1, C2, C4. So there was an index there, and DB2 said, well, you know, I don't like this index, but I'll use it anyways, and I'll read for matching values of C1 and C2, and I'll get myself a range of keys. Maybe I have to scan and include columns, or maybe I have to read rows from the table, but I'm not doing a row-by-row access anymore, so I don't have to write index for that. I'm doing a much less optimal index access feature. And, you know, you might get to this point and you might go, well, that's fine, but what if I didn't notice that? You know, what if I got to that point and I can't fix it? So the good news is you can call in experts by way of tools like DSM, the Query Advisor, and DSM. I'm a big fan of that, but even if you don't have that, you have DB2 Design Advisor. This command is shipped with DB2, right? And you can use this to get index recommendations, MQT recommendations, partitioning recommendations, etc. for your schema based on things like, you know, and give you results, you know, based on how your statistics are. Today, index is missing. And this is one that would have recommended an index, certainly based on what we had, and help guide you to the next step. Now, of course, you talk about index advisor, etc., and all its shortcomings, but it's still useful to have for cases like this. You can also be arranged to optimize for multiple indexes at a time, like all set or multiple statements at a time. Like, for example, all 7 statements, instead of playing whack-a-mole, optimizing one statement and it sacrifices another statement, and you know, like that. I can give it all 7 statements and have it work all at once, which is pretty good. With negative 1 minute and 36 seconds to go. Here we are. Okay, so I'll blame it on the 0.02 seconds of all right, so key to diagnosing where time is spent. I feel really strongly about that. I do this every day, and I use this approach every day. Mon report gets us started. It's a great thing, but we're going to have to drill down from there to some of the more complicated stuff. You definitely need to use delta values. Please don't forget that. If you're not sure where the bottleneck is at all, starting at the system level and working down from there is a good, safe approach. You know, we start off with the iceberg things, and the DB2s and the lows, and wait times, processing time varies simple stuff can help narrow down the problem really quickly. We've got wait time, we've got processing time. Knowing what the basic bottleneck type is really going to get us started in a deeper investigation. Statement level, we can end up there directly, or we might come there from database level, and the same principle applies. Where is time being spent? And again, statement explains, we have all the metrics, we have the same kind of time spent metrics that we have at the statement level, but eventually we're probably going to end up down having to look at explains. Getting the explain into DB2 LUW directly from the package hash is important to not being misled, based on this simple, almost cut and paste error from looking at explaining from a DB2 CLP section. And don't forget DB2 advise, and if you happen to have a DSM or other tools, there's ways to help you along this. Not very sense, but